So let's set the scene a little bit. Now we've referred to this schematic previously from Eddie Coyle, and we've really been concerned about the idea of performance velocity, and the idea that it's, in terms of endurance performance, it's can we get from point A to point B as quickly as possible. And we referred to in previous weeks in terms of economy of motion, we referred to maximal oxygen uptake. But notice, sitting in the middle, we've got these two elements referred to here as the lactate threshold power or velocity, or the lactate threshold VO2. Now, this is where, as you'll start to see, that the terminology and the language gets confusing. Eddie Coyle, in stating lactate threshold, is referring to what we are going to recall from in this session, and you need to use from now on, LT2. LT2. It gets confusing in a moment because we're also going to refer to an LT1, which is lactate threshold. He's referring to a lactate threshold at LT2, and we'll give you an alternate definition for that. But what he's identifying and suggesting is of importance as a functional ability is this point where you get a transition from predominantly aerobic to anaerobic metabolism. And this is really linked to what is called the fractional utilization. And the higher the percentage that the lactate threshold occurs as a percentage of the VO2 max, the higher the fractional utilization is. So if we've got an athlete who has this transition from predominantly aerobic to anaerobic metabolism at say 50% VO2 max, that means that they have not got a large aerobic capacity, and we'll define the capacity for you in a moment. So the higher this occurs as a percentage of VO2 max, the better it is for endurance performance. So we can define that both in terms of the absolute power of velocity, or in this instance as the oxygen consumption at that workload. Alternatively, we can define that, of course, in terms of the blood lactate concentration as well. But it is a fundamental parameter. Look at what it is closely associated to. Lactate threshold power or velocity is directly linked to performance power, which is linked to performance velocity. It's linked in itself to economy of motion, and it is directly linked to key physiological or morphological components that you can see across the bottom of this figure. So fundamentally, this is a very, very important point to us in terms of what we see here, endurance performance. Now, let's explain the capacity. And we're going to use the analogy of a high performance car. It could be any car, but a high performance car that you can see here, which is a very nice, I think it's a Ferrari F40. Now, if we think about cars and we think about Jeremy Clarkson talking about cars, he often refers to three big things. He refers to how big's the engine, okay? How fast does this car go? People tend to talk about the miles per gallon that a car can do. And people tend to think about, well, actually, how big's the fuel tank that we've got? So how many gallons of fuel can we take? And those are really three fundamental components that are used to define the performance capability of a car. We can transfer those across into these. So top speed is the engine, fuel capacity is the middle part, which is your tank, and then the miles per gallon, which is in essence how many miles can you do per gallon of fuel at a constant speed. And these can actually be translated very nicely for us in terms of endurance physiology. Maximal aerobic power is VO2 max. How big is the engine? So this is, in an example here, this is the top speed of a car. Ignore turbos, ignore using nitrous. It's the top speed of a car. How fast can it go? So this car can go, say, 210 miles per hour. What is the maximal aerobic power that the individual can go at? So, what's the maximal wattage they can produce aerobically, or the maximal running speed? And its associated oxygen consumption. Okay? It's associated oxygen consumption. So that's the top end capability aerobically, is the VO2 max. We have a fuel capacity. The fuel capacity in a car is the equivalent of our aerobic capacity. And the aerobic capacity is defined as either LT2, or what we're going to look at in a subsequent podcast as VT. LT is lactate turn point. VT is ventilatory threshold. It's how big is the tank to work aerobically? How big is that reserve? So the bigger the tank, the bigger the range. So remember I referred to previously about the fractional utilization. I suggested if you've got an athlete who's excuse me, whose lactate turn point, LT2, occurs at 50% VO2 max, their aerobic capacity is far smaller than an athlete whose LT2 occurs at 80% VO2 max. In other words, their aerobic range before they drift to anaerobic energy is far bigger. So this is a fundamental component of endurance physiology. The idea of this transition from predominantly aerobic to anaerobic metabolism. And then finally, something we've looked at in previous podcasts, miles per gallon, is performance economy, the submaximal VO2 response. So when we talk about miles per gallon in a car, we're referring to the miles that can be done for a gallon of fuel at a fixed speed. When we refer to the economy of an athlete, we refer to the submaximal VO2 response at a fixed speed or a fixed workload. These are the holy trinity of endurance physiology. The top end aerobic capability, the fuel tank, that is the lactate turn point, the aerobic capacity, and then the performance VO2, the submaximal cost of doing work. And these are all inextricably linked. And when we're defining endurance performance, it's about how we maximize these. You may find that you end up with an athlete that has not got a massive VO2 max, but they might have an aerobic capacity that occurs at 90% of that VO2 max with a low VO2. So in other words, you've got a not such good top aerobic speed, but very good submaximal data. You might have another athlete who's got a very high VO2 max, but maybe aren't quite as economical submaximally, but still have an aerobic capacity LT2, let's say 80% VO2 max. So it's about the confluence of these. It's unusual, although of course you might see it in the elite athlete, that you get all of these at their optimum. In most athletes, it's about making the most of these different attributes that we have. So let's go on a little bit of revision from a statement from George Brooks to kind of set the context in terms of the lactate data and what the lactate is showing us. So, as George Brooks writes, once thought to be the consequence of oxygen lack in contracting skeletal muscle, we now know that lactate is formed because it is a product of glycolysis. But lactate is utilized continuously under fully aerobic conditions. Remember we referred to this in a previous podcast on lactate as a mitochondrial fuel, and we referred to the notion that lactate that we record in the blood is the balance between lactate appearance and disappearance, and that the idea of disappearance really refers to the amount of that lactate that can be taken up in less active muscles and converted either to pyruvate or back to glucose. So it is not just this notion of it's a lack of oxygen. It's a much more complicated process, as we dealt with previously. Working skeletal muscle simultaneously produces and uses lactate as a fuel, as we've just suggested, with much of the lactate formed in glycolytic fibers being taken up and oxidized in adjacent oxidative fibers. Lactate disposal is mainly through oxidation, especially during exercise, when oxidation accounts for 70 to 75% of removal, and gluconeogenesis the remainder. So gluconeogenesis is the conversion of lactate back to glucose in the liver. The remainder, the vast majority, is taking place in the skeletal muscle. But this really sets that context for us about understanding why the blood lactate response to exercise is important, because it gives us that indication of the ability to produce lactate but also remove lactate, a fundamental part of endurance physiology. Remember, you don't want lactate, and in particular you don't want the hydrogen ions associated with lactate interfering with the mechanical machinery or mechanical mechanisms in terms of the muscles lengthening and shortening. So it's a fundamental measure. In a clinical population group, the same thing applies. We need to understand how big the aerobic capacity is, because this really reflects the zone in which individuals can do submaximal exercise. And if they've got a very low lactate turn point as a percentage of VO2 max, then what we've got is somebody who is who has very low submaximal physical fitness. And that may be either because they're just physically unfit, or it may be because there is some underlying pathology going on. I mentioned previously the terminology, and this is how it gets confusing for us. I've been referring to 2 points, lactate threshold and lactate turn point. So let's deal with turn point. So lactate turn point, as we've written right at the top in the grade, the workload corresponding to a rapid rise in the blood lactate indicating the equilibrium between lactate production and clearance. So in other words, exactly as we looked at in the previous podcast on lactate as a mitochondrial fuel, what you're measuring in the blood is used as a proxy indicator of the balance between production and removal. At the point of lactate turn point, just at that point before you get this sudden kick, there must be an equilibrium between the amount that's being produced and the amount that's being consumed, or the amount that's disappearing. So that's the lactate turn point. The lactate threshold, which is different, this is LT1, is the first workload at which there is a sustained increase in blood lactate concentration above resting values. And these are 2 obvious points that we can see on the curve. Now, I want you to use those definitions that are in grey. The definitions below have come from a majority of studies. Now, can you see how confusing this gets? Because under the lactate turn point, if you look third from the bottom, COIL defines it as a nonlinear increase of at least 1 millimole, but they refer to it as the lactate threshold. You could refer to it as the anaerobic threshold. Now, quite an old definition by Kindman, you can see a steep part of an exponential increase in lactate concentration, usually at 4 millimoles. The reason we don't use the term anaerobic is anaerobic as a term means without oxygen. But quite clearly, even if you go beyond lactate turn point, LT2, and yes, we're moving into a predominantly anaerobic zone, you're still using oxygen. You're still below VO2 max. So the term anaerobic is not appropriate, either if you look at the ADAPT definition, which is third from the top, or the anaerobic threshold by Kinderman. We've got an aerobic anaerobic threshold by Maida. Bit confusing in terms of that definition. We've got the OBLA, which some of you will have come across before, the onset of the blood lactate accumulation, and we'll look at that in more detail, and even what's called Dmax. I'll show you these graphically in a moment. The lactate threshold, which is this we define, and which is perhaps a better definition as this first rise, has also been referred to as the aerobic threshold, the lactate threshold, but defined 2 different ways: a point of deflection, the log blood lactate, or the workload producing a 0.4 millimole rise, a workload preceding a non-linear rise. It's been defined as a maximal lactate steady state, or the onset of plasma lactate. All of these are different definitions to define these 2 points. And you can see there's a lot of mess in terms of the overlap of these definitions. And that is why what we recommend you do is you make it very easy for yourself. LT2, lactate turn point. It's turning away from linearity. Lactate threshold, LT1, is the threshold where you get this first increase. It's a threshold. At that point, we've reached the threshold. Then it will level, as you'll see graphically, then it will turn away. So you have to be very careful when you read literature, when you read studies, or when you read textbooks, and they write, for example, lactate threshold. Do they mean lactate threshold or lactate turn point? Let me show you. Eddie Coyle has put lactate threshold, but actually what he means is lactate turn point. Okay, so that is the lactate turn point, is what he's getting at, LT2. It's just the taxonomy is very, very confusing. And so just be very careful about what it is you're referring to. So I'm going to, throughout the course of this podcast, refer to lactate turn point LT2 or lactate threshold as LT1. So here's some data which was from an elite middle distance athlete that we collected, in fact, in our labs here, doing an incremental test on the treadmill. And what you can see is pretty typical response. You can see the heart rate, which is the diamonds, and then the blood lactate concentration. So this was using 3-minute workloads with increments of speed of 1 kilometre an hour. And this is a very typical response. But what you can see is quite clearly there is that point that we've referred to in previous podcasts before, where we get this break from linearity there at 15 kilometres an hour. Can you see that up to 15 kilometres an hour, the blood lactate concentration shows a fairly linear response to exercise intensity? At 15 kilometres an hour, we suddenly get this sudden shifting away, this turning away from linearity. So that point there is lactate turn point, LT2. Go back to the definition. The workload corresponding to a rapid rise in the blood lactate concentration, indicating the equilibrium between lactate production and clearance. So just before that point, we've got a balance, haven't we? We've got a balance between production and clearance. Once we go beyond that point, can you see that the rate of appearance must be exceeding the rate of disappearance? Why do we know that? Because the blood lactate concentration has increased. But there is also a second point on this curve for us, or a second point of identification on this curve for us, and that is at 12 kilometres an hour. And 12 kilometres an hour, can you see that there is just a slight rise? In fact, the concentrations come down ever so slightly, but then you've got a slight rise before the concentration levels out. So it's at about 1.2 millimoles, then it goes to about 1.5, 1.55, then to about 2. That point there is the lactate threshold. The lactate threshold. And if we go back to our definition, the lactate threshold, the first workload at which there is a sustained increase in the blood lactate concentration above resting values. So you can see it's gone down and then gone up. So the point where you start to get the first rise is your threshold concentration, LT1. Where you get this sudden turn away is LT2. LT2 identifies the aerobic capacity. Beyond that, we're predominantly working anaerobic. So the aerobic capacity zone, or how big it is from 15 kilometers an hour backwards. So we can refer to this athlete as certainly having from 12 to 15 kilometers an hour a large aerobic capacity. So if it occurred at 13 kilometers an hour with LT1 at 12, they'd have a small aerobic capacity. We also would start to think about this as a percentage of VO2 max, as you'll see as we go through. But can you see how clear that is on the graph? It's not always as clear as this, but that's a pretty good indication of these 2 points. The lactate turn point, where the rate of appearance, beyond this point, the rate of appearance of lactate into the blood exceeds the rate of disappearance. The lactate threshold is where you get that first rise. So you get this first rise, and then you can see it's fairly level. We're getting lactate being produced, but it's certainly not a massively exceeding the rate at which it disappears. So these are 2 fundamental points, LT1, LT2.